Welcome back to Markov processes. When we last left off, we were talking about the concept of a limiting distribution for a Markov chain. We had a transition probability matrix, and we started taking higher and higher powers of that matrix, and we saw an interesting behavior. We saw that it appeared for that example that there was some kind of long run probability of the chain being in the various states of the state space, and that probability was independent of where we started the chain. Now, this is a very important and exciting topic in Markov processes, and I do want to get back to it. However, when I uploaded the last video, I realized that there was something in the previous lecture that I promised in the next lecture, which would have been the last video, that I forgot to come back around to. So I want to take a little bit of time at the beginning of today's lecture to come back to that topic. And that was the topic of simulation. Now, this course will have a little bit of simulation in it, and it is mostly near the end of the course. But I brought it up at this time, 2 videos ago, to make a point about running two Markov chains kind of in tandem. We had a chain called xn, and we created a new chain yn with the same transition probability matrix, but we made one state absorbing, and we said these chains will act the same until that special state is hit, at which time the Y chain will get stuck there and the X chain will continue to act according to an original matrix. And I wanted these chains to sort of run together with the same sort of random drivers behind them. So if they both started in some state, they would both move to the same state and sort of stay together until the special state was hit. Now, just having two chains like that running independently, just because they have the same probabilities of moving between states, does not mean they're going to actually stay together. Imagine having two identical fair coins, one in each hand, and they have the same probability of getting heads or tails. But if you start flipping them independently, you're not going to see the same outcomes for both coins. They just act the same probabilistically. But I was trying to make a point about those chains staying together if they had the same underlying random drivers. So I did an example 2 videos ago where we had just 2 points in the state space, 0 and 1. I had a 2 by 2 transition matrix, and I forgot to write it down again, but I believe that the 0 row of the matrix had probabilities 0.6 and 0.4. That is, if you're at state 0, you'll move to state 0 in the next time step with probability 0.6, or you'll move to 1 with probability 0.4. And I imagined us actually making those moves by having a crazy coin, or I might have called it a magic coin, probably crazy coin. And my coin was warped so that when I flip it, I get heads with probability 0.6 and tails with probability 0.4. And so if I'm in state 0, I'll flip that coin to figure out where that chain will go next. And starting at state 1, I had 2 probabilities in the 1 row of that matrix, and those were different than 0.6 and 0.4. So I had a second crazy coin. Now, we don't have usually crazy coins, or at least not too many of them, and that's not going to work for more realistic problems. So how would we sort of simulate actual values of the chain? By the way, if you have a random variable and you observe numerical values, we call that a realization of the random variable. For example, if I'm going to start rolling a fair 6-sided die and let X be the face I see, 1, 2, 3, 4, 5, or 6, then if I actually roll it, I will actually have a number for X, and we call that a realization of that random variable. If you are actually computing numbers for a Markov chain or any other type of stochastic process, which is really a whole collection of random variables at different time steps, then you can call those realizations of those random variables. But overall, as an entire collection moving through time, we usually call that a sample path for the Markov chain. So today, I'd like to start off by talking about how you might simulate a sample path for a Markov chain. It's going to be a very basic way to do it. There may be slicker ways to do it that we'll talk about later, but it all boils down to a random number generator. In fact, any sort of simulation algorithm involving any sort of randomness will boil down to a random number generator. A random number generator is an algorithm built into almost any software you can think of. Certainly, numerical scientific software packages, but even things like Photoshop has a random number generator. That's how you can blur images. You might have heard of a Gaussian blur, and that's where you sort of jitter all the pixels by adding some kind of noise to them. And that's done with randomness, which is done with a random number generator. Something like a spreadsheet like Excel would have a random number generator, but certainly anything you might be using for simulation like Python or R or MATLAB, anything like that. And so the goal of a random number generator is to produce realizations or observations for a continuous uniform random variable. So let me just remind you, I'm going to let capital U be a continuous uniform random variable on the interval from 0 to 1. I can include the endpoints or not include the endpoints. It doesn't matter for a continuous random variable because the probability of landing on those actual endpoints or any one particular value is always 0. We usually write U squiggly line, which can be read has the distribution, and then unif for uniform, and then 0, 1 in parentheses. You could put brackets here. You might not see brackets here, even if you do mean to include the 0 and 1, because this notation, this is not necessarily an interval, but rather parentheses that show you two parameters here, meaning the two endpoints of the interval, whether you include them or not. So a continuous random variable has an associated probability density function. For any continuous random variable, including this one, the probability of observing a U at exactly 0.3217732506973218, you get the point, is 0. There's just too many possibilities, and it's impossible statistically to land on one exact value. But this is where a probability density function comes in. It's a curve under which area represents probability. And for a uniform random variable, uniformity is like everything is equally likely. In a continuous case, we can't talk about the probability of landing on one point being the same as the probability of landing on another point. Actually, we can because those are both 0. But we instead talk about the probability of being in some subinterval of 0, 1 being the same if you slide that subinterval around as long as it's still contained in the interval 0, 1. So the PDF is a curve under which area represents probability, and we don't want it going up or down at all. We want it to be a flat line, and the total area under this line needs to be 1, so the height is going to be 1. Now, real quick, some probabilities. What is the probability that this random variable U is between 0 and 1/2 inclusive? It doesn't matter if I actually include those points. This is going to be the total area under this line between 0 and 1/2. This is a rectangle with base area 1/2 and height 1. So the probability is the area, which is 1/2. What is the probability that the uniform is between zero point 0.3 and zero point 0.4? Now we're looking at a skinnier rectangle with base from zero point 0.3 to zero point 0.4. So the base width is 0.1, the height is 1, the total area is 0.1. So that probability is 0.1. Just one more. I know you get the point, but I'm doing this for a reason. What is the probability that the uniform is between 0.17 and 0.37? Here I'm including the 0.17, but not including the 0.37. It's unimportant, but the base length of the associated rectangle is 0.2, the height is 1, the total area is 0.2, so this probability is 0.2. So a random number generator is going to produce realizations or observations or numerical values from the uniform 0, 1 distribution. And if it does this correctly, in the long run, we should see approximately half of our observations between 0 and 1/2, because the probability of seeing any one number from this random number generator between 0 and 1/2 is supposed to be 1/2. Now, you're not going to see any probability at all until you generate a lot of numbers with this random number generator. It's just like flipping a fair coin. If you flip it 10 times, there's a really decent chance you're going to see 6 or 7 heads in those 10 flips. That doesn't mean the coin is not fair. It just means you have to keep going for a while until you really get to see probability in action. The same thing is true for a random number generator. So the probability that a particular value produced by this is going to be between 0 and 1/2 should be 1/2. And you're not going to see that until you generate a lot of them. So, in the long run, generate many, many, many observations. Roughly half of them should be between 0 and 1/2. Exactly half of them if you generated an infinite number of observations. And 10% of them should be between zero point 0.3 and zero point 0.4 because the probability of being in there is zero point 0.1. 20% of them should be between the numbers 0.17 and 0.37 because, again, the probability of being in there is zero point 0.2. So we're going to be in there with that probability or that proportion of time. And a histogram of generated values using the random number generator, if you generate a lot of them and make a histogram, then you should see a kind of flat looking histogram. There's going to be a little statistical variability up here, but you're going to see something that should match the PDF as long as you are using the right quantity on the y axis of your histogram. I will get into this in great detail later in the course. But real quick, when you make a histogram, you are going to choose some bin widths, and then you're going to compute. Maybe you generate 100,000 values, and maybe this first bin here is like 0 to zero point 0.1, and then zero point 0.1 to zero point 0.2, zero point 0.2 to zero point 0.3, something like that. So you're going to look at the proportion in your 100,000 values that fall between those numbers and start building rectangles. The height of the rectangle could be the counts, the numbers of observations in your 100,000 realizations that fall in the associated bin, but that's not going to match the PDF. So we need to properly scale the y-axis. You could have counts up there, you could have proportions up there, or you can have something known as density up there. And what density does, again, I know I'm rushing here because I'm really not trying to talk about simulation at this point in the course. We will get into this in great detail, but density makes it such that the total area of the rectangle you make is the proportion of values in your generated values that you see in the associated bin. And that proportion of values in your 100,000 values that are maybe, say, between 0 and zero point 0.1 is supposed to be estimating the true probability of seeing a uniform between 0 and zero point 0.1. And so when the height is such that the proportion of values in your sample matches the area of your rectangle, that's corresponding to like area under a PDF curve being probability. So uh, yeah, I could have done much better with slides. I'm trying to not talk about this, but there's different ways to scale the y-axis. And if you do it right, then the histogram should sort of match up to that PDF at height 1. So how does a random number generator work? How is it producing these numbers? I am not going to talk about that here. This is a huge, huge topic. We could spend an entire semester talking about random number generators. It is totally off the mark for what I want to cover in this course, which is to talk about Markov chains. In fact, it doesn't even involve randomness. The random number generators are actually usually deterministic algorithms where you feed in a number and you put it through an algorithm and you get out a number, and it's so far from random. But people have, over the last 7, 8, 9 decades, been doing this really, really well to fake what appears to be IID, independent and identically distributed observations from the continuous uniform 0, 1 distribution. So there's actually no probability in most random number generators. They are deterministic, and there's definitely not independence between values. But if you have a good random number generator, again, you can fake it. And this is a huge, huge, huge topic that is so different from this course, so outside the scope, not outside of your abilities, but it's just a completely different thing. So I really hate having black boxes in any of my courses. And in the simulation we're going to do later, this is going to be the one black box, if you'll allow me to have one black box. Okay, so suppose that we have a random number generator, and suppose that we want to simulate observations for a random variable capital X that takes on, say, values 1, 2, 3, and 4 with probabilities 0.2, 0.3, 0.3, and 0.2. How can we do this? What we can do is break up the unit interval, the interval from 0 to 1, into an interval of length zero point 0.2, then an interval of length zero point 0.3, then another interval of length zero point 0.3, and finally we will be left with a remaining interval of length zero point 0.2. Now, if you grab a number using your random number generator that's supposed to be producing realizations of a continuous uniform 0, 1 random variable, for a continuous uniform 0, 1 random variable, capital U, the probability that it falls in this interval is simply the length of the interval, zero point 0.2. The probability it falls in the next interval here is the length of this interval, which is zero point 0.3. The probability that it falls in the next interval, which is an interval of length zero point 0.3, is again zero point 0.3, and so on. So when we actually produce a uniform using a random number generator, the probability it's going to be in these intervals corresponds to these probabilities. And so that's our recipe for outputting numbers 1 through 4. So here it is. Grab a value for u, the uniform 0, 1 random variable using a random number generator. If u is less than or equal to 2, I want you to output the value 1. Otherwise, if it's less than or equal to 0.5, and note the otherwise. So we've already ruled out it's not less than or equal to zero point 0.2. If it's up there in the next sort of chopped up interval, I want you to output the value 2. Otherwise, if it's in the next one, output the value 3. Otherwise, output the value 4. This is our first simulation algorithm to take a uniform 0, 1 from a random number generator and to turn it into something slightly more interesting. So let's get back to a Markov chain example from I believe this is actually from the last video, not the one before. We had a weather chain. We had some states, sunny, cloudy, partly cloudy, and precipitation. For what for our purpose today, I'm just going to call these states 1, 2, 3, and 4, but this is the same transition matrix that we had in our weather chain. Now, suppose we want to simulate a sample path of this Markov chain. What you need to do is start somewhere. And usually this is an arbitrarily chosen starting value. So I'm going to say x0 is 2. Now, if we're at state 2, then we need to look at the 2 row of the matrix. And you see there's some probabilities here, 0.2, 0.3, 0.3, and 0.2. This is no coincidence. These are the same probabilities we just talked about for the random variable we just simulated a couple of slides ago. So grab a value, a realization, and an observation of a continuous uniform 0, 1 random variable using your random number generator and compare it to the probabilities over here in the 2 row of the matrix. You can do this interval chopping approach where you chop up the interval from 0 to 1 into something with length 0.2, 0.3, 0.3, and 0.2. And by the way, they don't have to be in order like this. If you want to say, if the value, the u is between 0.27 and 0.47, then I will output a 1. You can certainly do that as long as you have the right probabilities. But for simplicity, let's just chop this interval in order. And so that's how you produce these values. This is exactly the previous simulation problem we just talked about. For concreteness, let's suppose that the uniform from the random number generator was 0.620331, rounded off. Comparing to these probabilities, that would put the uniform in here. And that means that we're going to output the value 3 to be the value of the Markov chain at time 1. In other words, x0 was 2. That was arbitrary. We grabbed this uniform, and now x1 is 3. So to go forward again, I am going to look now at the 3 row of the matrix because we're now at state 3. I'm going to grab a new realization or observation or numerical value of a uniform 0, 1 random variable using our random number generator. And I'm going to chop up the unit interval according to these probabilities in the 3rd row. And so you don't have to do them in order, but I'm going to go from 0 to 0.2 and then 0.2 to 0.4. So a second interval of length 0.2. And then I'm going to go all the way to 0.9 so that I have an interval of length 0.5 and the final interval with length 0.1. And so We're going to grab a uniform, and if it falls in here, we're going to output a 1, here a 2, here a 3, and here a 4. So let's suppose that the uniform came out to be 0.785610, something like that. Then according to these probabilities, we are going to again output a 3 because that's not between 0 and zero point 0.2. It's not between 0.2 and 0.4, but it is in the third interval that we're associating with the value 3. So now the next value of the Markov chain at time 2 is going to be 3. Okay, and so on and so on and so on. We can continue to simulate a sample path like this. And if we do this for a long time, and we do have to define what is meant by that, hopefully we will settle into a kind of equilibrium distribution for the chain, something like what we saw when we started taking powers of a matrix in the last video. We will come back to this. We will define long time, all of that sort of thing. But for this weather chain in the last video, we took powers of the matrix and we saw the columns settling down. In the first column, it appeared that all of the numbers were settling down to maybe 0.23. In the second column, 0.24. In the next one, 0.375, and so on. And actually, these are exact probabilities because I do have a way for us to exactly solve for these without just taking powers of the matrix and saying, I think it's good. We're going to do that eventually. But if you simulated this for a long, long time and grab the output out here at time, I want to say time 1 million, that's way too long for this sort of chain and way too short for other chains. We do need to talk about this sort of rate of convergence to this limit. But we should see the value here be 1 approximately 23% of the time, 2 approximately 24% of the time, etc. And of the time, what that means is you should start the whole chain over at an arbitrary starting value and grab new uniforms and run the chain forward and again collect output at this time step. And that is for the cleanest way to simulate IID values from this Markov chain because this can be expensive to start the chain over. Again, a lot of stuff I'm not saying right now because we're not really talking about simulation. I guess I am. Am I doing it or am I not doing it? I did not intend to talk about simulation yet. So we're doing it kind of in a rough way right now. But yeah, so that's it. I think I filled in the hole from 2 videos ago where I said we don't have crazy coins or magic coins, but we instead might have a random number generator. And this is how you can simulate simple discrete random variables, which translates to simulating sample paths for Markov chains on a nice discrete finite state space. Okay, so in the last video, we were talking about this limiting distribution, and my ultimate goal is to give you a theorem. So you can say for your Markov chain, if my chain satisfies this and this and this, then those are sufficient conditions for me to know that there's going to be a limiting distribution and that it's not going to depend on where I start the chain, because there are more complicated Markov chains where you can't just take powers of the matrix and see that nice behavior, but you're going to want to know that it's there. And to this end, to get to this, I have a theorem coming up for you. It's probably still a couple lessons away. And that theorem will give you sufficient conditions for that limiting distribution. We're trying to build up a bunch of notation, terminology, definitions, and some lemmas to build up to that theorem. So in the last video, we looked at Markov chains that broke down into communication classes. And communication classes were collections of states from the state space where all states communicate. You can get from any one state to any other state within a class. And we saw that you could move out of one class into another class, but then you wouldn't be able to move back because if you could, then all the states in both classes would communicate. And so they should have been in one class to begin with. And we talked about states being recurrent or transient. Recurrent states are states that when you start from a recurrent state, you will return again. It might take a long time, but you definitely will, with probability 1, return again. For a transient state, you may return, and you may return several times but eventually you're going to find your way to a part of the state space where you can't return to that starting state if it is transient. And these two concepts, recurrence and transience, are key components to talking about a limiting distribution for a Markov chain. And that's what we were in the middle of discussing. So, right now, I'm going to do what seems like another aside to talk about a distribution. But the reason we're doing this is that for a recurrent state, we're going to return and we're going to return again by the Markov property. When you return, you are kind of starting over because say you're at some state I, if it's recurrent, and you move the chain along, eventually, if it's recurrent, you'll return to I. Once you come back to I, the past history no longer matters, and going forward, you will eventually return to I. For a recurrent state, we're going to keep coming back again and again and again. For a transient state, we may keep coming back for a while, but I want to talk about the expected number of times that we'll return to a transient state before being lost forever into another part of the state space. And to do this, I need to remind you about the geometric distribution. So, geometric distribution, forget about Markov chains for the moment. The setup is that you have repeated independent trials of an experiment. And each trial of the experiment has one of two possible outcomes that are usually called success or failure. And I'm going to denote them with a capital S and a capital F. Then we have a parameter lowercase p, which represents the probability of success on any one trial. Being a probability, this lowercase p has to be between 0 and 1 inclusive. Finally, I'm going to let x be either the number of trials until the first success or the number of failures before the first success. Now, both of these random variables are said to have a geometric distribution with parameter p. And people usually write capital X, squiggly line has the distribution geom, open parentheses, p, close parentheses. Sometimes people will write the whole word geometric and not just geom, but they'll write this when they mean one of these two random variables. Note that this first one up here potentially starts with the value 1, because how many trials is it going to take you to see the first success? It could be one trial, it could be two, it could be three. There's really no upper bound, but the possible values that X can take on here are 1, 2, 3 on up. Whereas for this formulation of the geometric distribution random variable, the number of failures before the first success could be 0 if you see success right off the bat in your first trial. So I personally, this is not a notation that you're going to see out here, but I like to change this notation up a little bit, and I like to put subscripts on the geom part. So a geom sub 1 or a geom sub 0 to indicate the geometric distribution that starts from 1 versus the geometric distribution that starts from 0. And in what we're going to do today, we're going to need the one that starts from 0. So let's look at that one a little more closely. Let's let X be the number of failures before the first success. X takes on values in the set 0, 1, 2 on up. What is the probability that X equals 0? This means there are 0 failures before the first success, and this means we see success right off the bat in the first trial, and that happens with probability little p. Now, what is the probability that X equals 1? This means there's 1 failure before the first success, so this means we see a failure on the first trial and success on the second trial, and the trials are assumed to be independent, so we get to multiply the probability of seeing a failure on the first trial with the probability of seeing a success on the second trial. The first probability is, the success probability is p, and the failure probability is 1 minus p. And this probability is not changing based on the number trial that we're on. So we simply get 1 minus p times p. Okay, so the probability that X equals 2 means we're seeing exactly 2 failures before the first success. So that's going to be failure and then success. We're going to get 1 minus p times 1 minus p times p. But in general, the probability that X equals some little x is going to be 1 minus p raised to the x times p, as long as X is 0, 1, 2 on up, and the probability is going to be 0 otherwise. We're not going to see, our random variable X be 1.7, or we're not going to see it be negative or anything like that. only the possible values right here, and the other probabilities are 0. So again, I'm going to write x squiggly line has the distribution geom sub 0 of p, and this is a probability mass function. You have probably seen this before. If you're in here, you've probably had a course in probability, and hopefully you have talked about expectations before. The expected value for this random variable is usually denoted by a capital E of x, and it is the sum over all little x of little x times the probability that capital X equals little x. Now, this is a more general definition for expectation for a discrete random variable, and I just put summing over x, and I didn't say x equals something to something, like if I put minus infinity to infinity, that looks like I'm talking about integers. A discrete random variable does not have to be integer valued. So I like to write my sum like this. But for this particular distribution, the sum does go from 0 to infinity. So I get the sum as little x goes from 0 to infinity of little x times this probability mass function. And we want to sum this up. I'm going to pull out the little p. I am going to take one term out of this sum. Note when x equals 0, this summand is going to be 0. So let's just sum from little x equals 1. And to sum this up, if you know how to sum this up, then ignore what I'm about to do and what I'm going to do on the next slide, because I might just make it harder for you. If you can do this sum any way you know how. But if not, I would suggest pulling a single 1 minus p outside of this sum. Why am I doing this? What I'm going to do now is call this 1 minus p, I'm going to call it q. At this point, I have the expected value of x equaling p times 1 minus p times the sum as little x goes from 1 to infinity of x times q to the x minus 1, where q again is 1 minus p. And the reason I pulled out a 1 minus p, or equivalently a q, is because this now looks like a derivative. If I had to do this sum without the x, it's a simple geometric sum, but this x in front makes it more difficult. If you are into memorizing formulas for sums, then you might know this. I am not good at memorization. I tend to derive all of my sums from a basic geometric sum. And so this looks like the derivative with respect to q of q to the x. And if you note that, you can pull the derivative outside the sum. So derivatives and sums are interchangeable for a finite sum. This is not a finite sum and does take some care. I don't want you to worry about it for this course. I just would rather focus on the Markov stuff and not things like this. But yes, with an infinite sum, you could have an issue here, and you would really have to invoke something like the dominated convergence theorem from analysis. But if you don't know what I'm talking about, please don't worry about it. We have other things to worry about that are far more interesting to the subject of Markov chains. So I'm going to interchange the derivative and the sum. And now I am left with a geometric sum. You might be used to like an r to the n. This is a q to the x. If your n in that case started from 0, then the sum would be 1 over 1 minus r, as long as r is in magnitude less than 1. But this sum starts from 1, and you need to adjust things a little bit. So I'll let you take care of that. But this sum is q over 1 minus q. I'm going to take the derivative. I'm going to use a quotient rule. I'll get the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And then when simplifying this, everything cancels down to a final expectation of 1 minus p over p. So that is the expected value of the geometric random variable that starts from 0. If we did this for the other geometric distribution that starts from 1, we should get 1 over p. Okay, so back to recurrence and transience. And I need a few more definitions. So to get back to recurrence and transience, I want to talk about first hitting times and first return times for a Markov chain, or more generally for a stochastic process, even if it doesn't have the Markov property. For us, I'm going to let xn be a Markov chain, and I'm going to define a first hitting time on state I. I'm going to call this capital T sub I, and this is going to be the minimum over all integers n greater than or equal to 0 such that xn equals I. So is x 0 equal to I? If so, we have hit state I at time 0. If not, look at x1. Is that equal to I? If so, and it was not equal to I at time 0, the first hitting time on state I was time 1. And in general, this is a random variable, so I'm using a capital letter. A second thing I want to define is a first return time to state I. This is often also denoted by a capital T sub I, which can be confusing. I often use my own notation when I think things are going to be too confusing, but I also try to balance that with not steering too much away from standard notation. So I'm going to use T sub I for both of these, and hopefully it will be fine in the context of the problem we're talking about. But a return time means that you started at I and then you want to come back to it at a time greater than or equal to 1. So you'll notice here that I have a minimum over all integers n greater than or equal to 1, such that xn equals I. Now that alone is not a return time unless we are in the context of starting at I, because just because you hit I at a time greater than or equal to 1 doesn't mean you return to it unless you had started from it. So a first hitting time, we start looking at time 0. A first return time, we start looking at time 1. But for the first return time, it's always in the context that the chain has started in that state, in this case, state I. Okay, so now that we have definitions for hitting times and return times, we can more formally define recurrence for a Markov chain. I'm going to let capital T sub I be the minimum time at times greater than or equal to 1 that we find the chain in some state I at time n. I'm going to define a probability that I'm going to call lowercase g sub I. I know, why not p sub I? There's just way too many p's floating around in this course. I'm going to call it lowercase g sub I. I'm going to let this be the probability that T sub I is finite, given that we're starting the chain in state I. So now, because we're given this information in this context, this is a first return time to state I, and this is the probability that a Markov chain starting in state I will return in finite time. And you can actually say it will return at least once, because once it returns, well, we have to start over from there using the Markov property, and we'll get back to that. But this is the probability that the chain starting in I will return in finite time at least once. And with this, we have a definition of recurrence, a formal definition. So state I is recurrent if and only if this probability of returning at least once is 1. On the other hand, the state I is transient if and only if this probability of returning at least once is less than 1. So I've got some new notation for you. I'm going to let T sub j, this is not new notation, I'm just using a different state. I'm going to let T sub j be the minimum time to hit state j at times greater than or equal to 1. This may be a return time if we start the chain in state j. That's not new notation, just a new state. But we're going to start using subscripts on probabilities and expectations to represent the Markov chain's starting values. For example, if you see a capital P sub I of T sub j equaling n, this is defined to be the probability that T sub j equals n, given that the chain at time 0 started in state I. Again, a subscript on a probability or expectation is telling you that you are starting the chain at this subscript and you are working in the conditional universe that the chain starts in this case, state I. So P sub I of T sub I being less than infinity, by definition of this new notation, this is the probability that T sub I is less than infinity, given we're starting the chain in state I. This is now a first return time to state I in this context, and this is how we just defined our G sub I. And just one expectation example, the expectation or a capital E sub I of T sub j, the definition of this notation means find the expected value of T sub j in the conditional universe where x0 equals I. And if you have to compute this, you would sum over all n. In this case, n would be 1, 2, 3 on up because those are the kinds of values that tj could take on. And you would take n times the probability that t sub j equals n, given that x sub 0 equals I. That's how you would compute this conditional expectation. It's just summing the values times the probability while staying in a conditional universe, so while using conditional probabilities. And I could rewrite this conditional probability using this notation up here. Now, what is the expected number of returns to a state for a Markov chain? So everything I'm doing here, I want to start with a Markov chain on a state space, and it's defined and it's called, x sub n with brackets around it. We are talking about Markov chains here. And returns implies that you're starting at the state. Case one, a recurrent state. We've really already talked about this, but let's just recap really quick. So starting at a recurrent state I, you will return with probability 1. So starting at I, you eventually come back to I. And now, going forward, using the Markov property, the fact that you're at I is important, but not how you got there. You're starting at I again. And so you will eventually return again because I is a recurrent state. And you're going to return again and again and again. And you are going to return to any recurrent state infinitely often. But if I is transient, that's where things get a little more interesting. If I is transient, starting at I, there is some path away from I into another communication class where you can never get back to I. But that doesn't mean you're going to take it right away. You might be in that communication class for a while, revisiting I before you escape forever. So, my question for you is starting at a transient state I, how many times do you expect to return to I before you escape, never to return again? This is what we want to compute in the rest of today's lecture. So I'm going to let I be a transient state. I want the expected number of returns to I, given that we're starting at I, so I should use better notation here. Let's set it up. I'm going to let capital N be the number of times the process hits state I at times greater than or equal to 1. So I'm not even using return language here. I'm just talking about hitting I at times greater than or equal to 1. And we want to find the expected value of n, given that we're starting the chain at state I. But I can do you one better than this. Not only can we find this expectation, we can find the distribution for n in this conditional universe where x0 equals I. And if we find the distribution, we can also then find the expectation. So let's do that. Let's first consider the probability starting at I that n is greater than or equal to 1. Just as a reminder, because this is new notation, this is the probability that n is greater than or equal to 1, given that x0 equals I. So n is the number of times we hit I at times greater than or equal to 1. So n being greater than or equal to 1 means we have at least one return to state I, given that we started at I. And this probability, we call this lowercase g sub I. So what is the probability starting from I that n is greater than or equal to 2? This is the probability of at least 2 returns to I. And if you start at I, how do you get at least 2 returns to I? You have to have at least one. So imagine a sample path starting at I, it has to come back around to I, and then it has to do that again. And using the Markov property, once you reach this state I, where you go next does not depend on this stuff back here, on how you got to I. So we have an independence here. It's not that each value of the Markov chain is independent of where it was in the past, but once you have a fixed value, we do have independence of, where you go next versus how you got to that fixed value. The answer here, the probability starting at I of at least 2 returns to I, is the probability we return one time, g sub I, times the probability we return to I again, starting from I at this time step. This is using the Markov property and the idea that our Markov chain has independent increments. It doesn't have values being independent of the previous value, but how you get there, sort of independent of how you got to that previous value. We get g sub I squared. So continuing in this way, The probability starting from I that we return at least 3 times is g sub I cubed, and so on. I want to find the actual distribution for n, given that we're starting the chain at state I. So starting at I, the probability that n equals 0, I can write this as the complement of the event that n is greater than or equal to 1, all while staying in this conditional universe that we started at I. So notationally, this is 1 minus capital P sub I of n being greater than or equal to 1. And this probability in here was g sub I, so we get 1 minus g sub I. Whereas the probability starting from I that n is equal to 1, I can write this as that probability in that universe where we started at I that n is greater than or equal to 1, but take away all the stuff that says that n is greater than or equal to 2, we get g sub I minus g sub I squared, and we could factor out a g sub I to get g sub I times 1 minus g sub I. Similarly, the probability in this universe where we start at I that n is equal to 2, we can write this as the probability that it's greater than or equal to 2, but take away all of those times where n is actually greater than or equal to 3, we get g sub I squared minus g sub I cubed, and we can factor out a g sub I squared. So we're starting to see a pattern here. And in general, starting from I, the probability starting from I that capital N equals n, this is g sub I to the nth power times 1 minus g sub I. And n here is allowed to be 0, 1, 2 on up, because starting from I, we're counting the number of returns to I, and it's possible we never return. And it's possible we return only 1 time, only 2 times, and so on. We really don't have an upper bound on that. What this is telling you is that the random variable n in the conditional universe that we start the chain in state I has a geometric distribution. It is the geometric distribution that starts from 0. So I'm going to say geom sub 0. But if you try to match this up with the geometric probability mass function that we derived in today's lecture, you'll see that the p parameter for this geometric distribution is actually 1 minus g sub I and not g sub I. But in particular, the expected value that we wanted, the expected number of returns to state I, given that we started at I, this was 1 minus p over p for a geometric distribution starting from 0. And translating, because p is 1 minus g sub I, this is g sub I over 1 minus g sub I. Now, if I is transient, g sub I, by definition of transients, g sub I is less than 1. So we don't get a 0 in the denominator, and we get that this is a finite value. The expected number of returns to state I, if we start at state I, and if state I is transient, is finite and is equal to this value here. And maybe we have to compute this probability to find it, but we have something finite. And by the way, this formula kind of works in the recurrent case as well. Now, if g sub I is equal to 1, we have a 0 in the denominator and things are undefined. But if you think of it as g sub I is approaching 1, then this denominator is approaching 0 and getting larger and larger and blowing up to infinity, which is the kind of behavior you would expect for a recurrent state. The expected number of returns should be infinite. So yes, we don't want a 0 in the denominator, but if you let g sub I approach 1, this thing is blowing up to infinity, and that is what you're expecting from a recurrent state. So we are almost out of time here. In the next lecture, we are going to talk about alternative ways to characterize states as recurrent or transient, which can be really helpful when you don't have a nice, small, compact, finite state space where you can just follow arrows around and say, this is transient because I see an escape route. So we'd like a mathematical way to characterize it. We sort of have one today, but we need to compute that g sub I probability. We're going to talk about examples of that in the next lecture, and also an alternative way to determine whether something is recurrent or transient if you can't actually compute that g sub I probability. Why are we doing all this? We still have the short-ish goal that's still going to take a couple of videos to have a nice theorem that says, given that you have states that are recurrent, maybe all your states are recurrent, that is one of several conditions you would need to get a set of sufficient conditions to have a limiting distribution for a Markov chain. So that's why we're talking about this stuff right now. And we'll continue. next time on Markov processes.